this video, we're going to continue doing something that we've been doing for many weeks now. We're going to solve differential equations, but we're going to get a little bit more formal about solving those differential equations. So first question we would want to ask is, what is a differential equation? And it's as obvious as the vocabulary terms themselves. A differential equation is an equation involving a derivative. So you see in the two examples a set of, edit, undo, differential equations because they are equations involving a derivative. Now, when you solve a differential equation, you're simply going to find the antiderivative. You're going to go back to where you came from. But as I said, it's going to get a little bit more formal because most of the antiderivatives that we have been solving involve something like x squared plus 2x minus 1 dx. Notice it wasn't an equation, it was an expression. You were given the derivative and you found the antiderivative going back to the original function. How is this different? Well, first of all, they didn't give you an antiderivative from the beginning. They gave you an equation. So the first thing that you're going to do, notice we have a dy and then we have a dx, and we have on the right hand side an expression that is in terms of x and an expression that is in terms of x. So the first thing we're going to do is we're going to get all of the like variables together. So I'm going to multiply both sides by dx, and when I do, if I multiply this side by dx, and I multiply this side by dx, I will get dy is equal to x plus 4 over 2x squared dx. So all I did initially was to separate the variables. Now, the golden rule of algebra is whatever you do to one side, you must do to the other. And to solve this differential equation, we're going to have to find the antiderivative, but we have to do it to both sides. On the left-hand side, it seems like there's nothing there, but you know better than that. You know that there's an understood 1 dy on the left-hand side. So on the left-hand side, we will find the antiderivative in terms of y, and on the right-hand side, we'll find the antiderivative in terms of x. So when we find the antiderivative in terms of y, if we find the antiderivative of 1, we get y. And on the right-hand side, that's the same thing as x. Let's pull the 1/2 out front. This is my scrap work over here. 1/2 over x plus 4 over x squared, which is 1/2 the integration of 1 over x plus 4x to the negative 2 dx. That's the same thing as 1/2 ln absolute value of x. Increase the power by 1. So that's going to give me 4x to the negative 1 minus 4, and then my plus c. So 1/2 ln absolute value of x minus 4 over x plus c. So notice I just took the right-hand side over here, pulled the 1/2 out front, did a little bit of algebra work, and found the antiderivative. Now, the first question that usually pops up in all students' mind is, okay, I get the plus c on this side. What about the plus c on the left-hand side? This is going to greatly disturb you, but c is a constant. And so technically, I would have a constant on the left-hand side and a constant on the right-hand side. I can move the constant on the left-hand side to the right-hand side and simply make one constant, a plus c. I know this greatly bothers you and that there are lots of questions about that we can address more thoroughly in class, but for now, suffice it to say that when you do the plus c, you're going to do the plus c on the x side of the equation. Again, we can talk more about that in class, about the whys and the hows and all of that good stuff. But bottom line, I think you can see that we really have been solving differential equations for a while now. All right, let's take a look at another, well, before we take a look at the example, let's record the steps to solving a differential equation. So in that problem, notice that the first thing that I did is I separated the variables. I got all of the x terms on one side and the y terms on the other side. The second thing that I did was I integrated both sides of the equation. The x side I integrated with respect to x, and the y side I integrated with respect to y. And as I said, we're going to do a plus c on the x side. Now, the last problem didn't involve this, but if there is an initial condition, I'm going to solve for c if possible. And to do that, I have to be given an initial condition, and then I'm going to solve for y. And sometimes steps 3 and 4, the order in which we do that depends on the problem. So that's all I'm going to say about that for now until we encounter um, the scenario that I'm thinking about. All right, so problem example number 1. We're going to solve the following, which means we're going to find the antiderivative. So the first thing we're going to do is separate the variables, and notice that this time I have a y and an x and an x. So all of the x's on one side and all of the y's on the other. So I'm going to multiply both sides by dx. So I get dy over y is equal to 3x squared dx. So I multiplied both sides by dx, and I divided both sides by y. Now, it may be more helpful for you to see that written as 1 over y dy is equal to 3x squared dx. And then, when I have the variables separated, I'm going to find the antiderivative on both sides. So this is the antiderivative of 1 over y is ln, absolute value of y, equal to 3x cubed over 3 plus c. Now, in solving, there's no solving for c because they didn't give me an initial condition. But in solving for y, it's going to be very algebra intensive. To solve for y, remember that there is an understood base of e for ln. I'm going to take this out of log form and into exponential form. So I'm going to have e raised to this power. So I have y equal to e raised to the x cubed plus c. You may be wondering where the absolute value went. Well, e raised to a power is always a positive value, so I don't have to worry about the absolute value anymore. Now, let's take that a little bit further using more algebra. That's the same thing as y equal to e to the x cubed times e to the c. That is a property of exponents. Remember, when you have like bases, you keep the base and add the exponents. Well, I'm just decomposing that. Why am I doing that? Well, e to the c, e is a constant, c is a constant. A constant raised to a constant is simply a constant. So I'm going to rewrite this as y equal to c e to the x cubed. Okay, so study that algebra from here to here. Lots of algebra, and most of it is dealing with changing from exponent form, log form to exponent form, and using properties of exponents. All right, let's look at the next example. Y prime I'm going to change into dy over dx equal to 3x squared over y. I'm going to get all of the y terms by multiplying both sides by y, and get all the x terms together by multiplying both sides by dx. I'm going to find the antiderivative of both sides. When I find the antiderivative of y, I get y squared over 2. Whoops, see, I'm such in the habit of putting plus c. I put it on the y side. On the right-hand side, I get x cubed plus c. Solving for y, I get y squared is equal to 2x cubed plus c. Again, I know that drives students batty because 2 times a constant is a constant. Students want to write 2c and they get all freaked out by that. But again, a constant times a constant is a constant. So y equal 2x cubed plus c, and y is equal to plus or minus square root of 2x cubed plus c. That is my original function. And now we have one with an initial condition. So we're going to separate our variables by dividing both sides by y squared and multiplying both sides by dx. That's the same thing, excuse me, as y to the negative 2 dy, 2x dx. So that's going to give me negative 1 over y equal to, I found the antiderivative using the power rule, increase the power by 1 and divide by the power. On the right-hand side, I have 2x squared over 2, so I have x squared plus c. I'm going to go ahead at this point and substitute the 0 and the 2, 0 in place of x and 2 in place of y to solve for c. So that'll give me negative 1/2 is equal to 0 plus c. So c is equal to negative 1/2. I'm going to come back to this step, substitute the value of c. I get negative 1 over y is equal to x squared minus 1/2. Remember, I'm trying to solve for y, so the first thing I'm going to do is multiply everything on both sides by negative 1. So I get 1 over y equal to negative x squared plus 1/2. I'm going to get a common denominator on the right-hand side, so that'll give me negative 2x squared plus 1, a common denominator. And now, since I have one fraction equal to one fraction, if one fraction is equal to one fraction, the reciprocals are equal to each other. Oops. The reciprocal, oops, come on, eraser. So in other words, I can flip those fractions. So all I did was flip this side to get y by itself. And also, I know some of you will be wondering what happened. I just switched the order of these two terms so that my first term was positive and made that 1 minus 2x squared. Okay, again, a lot of algebra, a lot of fractions. Number 4, the rate of change of v. The rate of change of v. Well, we got to do some translation. Rate of change of v would be dv dt. Not a related rate. Well, I mean, it kind of is, but we're going backwards. The rate of change of v with respect to t is proportional, so we have our is, turns into equals, proportional to direct variation, 300 minus 3t. Remember, back in Algebra 2 days, y varies directly as x, means y is equal to kx. K is a constant of proportionality. And so all we're actually doing here is simply translating this expression, and we're going to do more with that when we get to the applications of differential equations.